Hey, hello, my name is Tobias, and today I want to show you how you can gain speed in space with NLP and Solr. As you might mention, I just renamed my talk to Gain Speed and Precision with NLP and Solr because I think it's a more interesting topic in this talk. I first want to start with some basic information about me. I'm husband, father of two beautiful children. I'm from Hamburg, and I'm working in Hamburg for Shopping24. And also the initiator and organizer of the Search Technology Meetup in Hamburg. So if you visit Hamburg, feel free to join the meetup, feel free to learn something about search technology. The next meetup will be on Wednesday, and we're having a great time with two talks from the Berlin Buzzword and a third talk from eBay Kleinanzeigen. If you have free time, if you are in Hamburg, feel free to join. Yes. I want to start with information about Shopping24, what we do. Basically, Shopping24 is a product search website. So we do not sell any product. We just deliver traffic to shops. And we've got a lot of different websites where we show products to our customers. In our backend, you will see on the left side, we're basically using Apache Solr as a search engine. We're using Spring for our API. We're using Postgres for all of our backend processes, Varnish and GitHub for our projects. In the last year, our management team came around and said, OK, we've got a new requirement for our backend team, and we're currently absolutely fine with 3 million products on our website, but in the next year we want to scale up to 100 million products. And we're in our backend team sit together and we're like, okay, that's going to be a hard challenge, but we saw three problems. We saw the disk space of our Solr indexes explode. We saw the precision in our search result, because when you throw another 97 million products into the search index, what happens with the precision in our search result? Does it preserve? Does it increase, decrease? What happens? And we currently have no sharding. We're now working on it, but it's really hard to manage all of these products. We sit together, and we finally came out of this meeting, and we say, OK, we have to reduce, as a first step, our data. We have to reduce text to do not store the whole text that we've got in our products. We store products, and they consist of title, description, product metadata, attributes, price, something else. And we saw two simple winnings ahead when we do the reduction of the text or the index data. We saw that the speed will increase and the space, because due to fewer index terms in our index. So I want to show you in this presentation, in this short talks, just two solutions, how we do this. How do we reduce the text? And the first solution is just for product descriptions, and the second solution is for usual text. So we take a look into our products in our data that we store in Solr, and we saw that a usual description consists of about 95% of irrelevant text, or we named it SEO text. So we've just a very, very small amount of relevant text. And this is pretty bad for a search engine, because every token that is in the SEO or irrelevant text is a signal for our search engine. And so we finally figured out SEO text equals evil equals not relevant or irrelevant. What do we have in our descriptions? We have a lot of sentences like, OK, we have here really good-looking blue jeans, and you combine these blue jeans with a great red T-shirt with blue stripes and something else. You can sit on your couch and enjoy this television with a friend, so on, so on. We've got a lot of text that is not relevant for a search engine. And we're in a team, sit together and thought about, OK, how can we filter out these bad sentences? And we are like, okay, there are really good stuff out there. Okay, we can use the open NLP framework with a lot of great algorithm implementation. We can use SVMs, we can use deep learning technologies, we can use neural networks to train a model and that differ between good or bad sentences. We can use keyword extraction, but we're ended up with a much, much more simpler solution. We place this solution into the last step here in the Solr indexing process. And this is our whole product pipeline at Shopping24. So we just gather the data from our customers. We do some basic pre-procession, some normalization. And after that, we do some named entity recognition where we just recognize entities that we know. But you can, we also want the unknown entities in the description, so we have to use them as a signal for our search engine. We named our component the analyzing sentence tokenizer, and we placed it in a third step at in our Solr indexing process. So we've got a field type that is called text. We first do some basic HTML strip-char to get rid of all of the HTML text. Then we do duplicated white space removement. That's pretty simple. And then comes the analyzing sentence tokenizer, which has the one and only required argument, a list of stop words. And here's how it works. It's so pretty simple because it relies on the key assumption that sentences in product description with useful information do not contain a lot of stop words. So how it works. Here we've got a description from a product. We just do another basic cleanup. In this cleanup, we do some things to get a better analysis, to get a better sentence tokenizing. We split the description into sentences, and then you've ended up with a simple list of sentences. Just iterate over these sentences, and here comes a little helper. If the sentence contains a lot of signs means if the ratio of the signs is above a given threshold, then you have to split the sentence again. This is a little helper to get rid of all of the bad data we get from our customers where no punctuations in any description or something like that. And after that, you've got the completely splitted sentences and just build a ratio between the stop word count and the word count. And check if it's under or above a given threshold. And this works pretty well. So we've got three learnings. And the first learning was that for the sentence tokenizing process, we've got a first version of the sentence tokenizer where we use the sentence tokenizer from the open NLP framework, and it delivers a really, really good quality. But it's absolutely not as fast as a regular expression. So this is our sentence tokenizer. We do not use any fancy stuff. This is our, this is it. And the other learnings are that you do not have to analyze text that is just one sentence. If you have any just one sentence, pass it through, except you have to split it again. So this is a very simple approach, and we finally ended up with a word reduction in our descriptions of about 60 to 80%. And the precision of our search result preserves, or if not better, increases due to this simple stuff. Yeah, but what happens if you do not have any product description? Because in a product description you can define bad sentences by the ratio of a stop word in a sentence. What happens if you have usual text? Here's an example from Wikipedia, the Apache Solr entry. And what happens if you use the analyzing sentence tokenizer to analyze these sentences? He will throw away all of these sentences. This is pretty bad. But what happens if you also want to reduce the data? If you just want to store the relevant text or the relevant keywords of a text? we're using another component, the rake algorithm, and this is just another Swiss Army knife for you to get home with. And I want to show you a really short example how the rake algorithm works. Here's the first sentence of the Apache Solr Wikipedia article, and the rake algorithm works as following. He uses the stopwords and punctuation as boundaries for keyword candidates. So you can see you've got the keyword candidate Solr, open source enterprise search platform, written Java, Apache Lucene project, and is and in from the are stopwords or the boundaries and the punctuations. After that, he calculates a score for each candidate. So imagine you have a really large text. This makes a lot of more sense, but this is just an example. He calculates a score for each candidate and returns 1/3 of the top candidates as keyword results. So this is pretty simple. Not a lot heuristics needed, and it works absolutely good. We use the rake keyword extraction algorithm to, with 2.5 enhancement, we define, or when you use it, you have to define your own stopwords, your domain-specific stopwords. You couldn't use just the usual stopwords that are flowing around like this, that, and, or, something like that. You have to define additional word types like verbs or something like that. You have to define more signs or URLs if it fits into your domain of text. And we've implemented another feature into the rake algorithm. We propagate score from overlapping or related keywords. So what happens if you have the text and you extracted the keyword Hugo Boss and the keyword Hugo, and you have a score for each keyword, you can propagate the score or multiply a factor into each other keyword because you know this is an overlapping keyword. This will bring you to a much better score calculation of the rake algorithm. And after all of our keyword extraction algorithms, we use an additional filtering of the extracted keywords. So this is a half enhancement because I think it's very common. Yes. The Analyzing Sentence Tokenizer is available for free at shopping24/Solr-Analysis. If you have any questions, you can mail me at work@tobiaskässmann.de or visit the developer blog of Shopping24, developer.s24.com. And that was my talk about how to gain speed and space with NLP and Solr. I think I was a little bit faster as previously thought. Yeah, thank you. Are there any questions?
Well, thank you for your insightful and fast talk.
Yeah.
You mentioned that it's helpful to have kind of domain-specific stopwords. Could you give an example of what you mean by this?
Yes. So we've got a lot of texts that are coming from our partners. So okay, I can give you an example where we use this rake algorithm. When we've got a website with a long-running text and you want to show products to that text, we just get the text, let the rake keyword extraction algorithm extract the keywords, and then throw the extracted keywords just into our search engine. This is pretty good. This works pretty well. And in that case, we define a lot of verbs as stopwords. So we just do not have these usual stopwords like this, and, or, something like that. So you can use other word types like nouns, verbs, but they are absolutely domain specific. So
Do you have access to query logs?
Query logs?
Yeah, because I think from that you can like gain a lot of information, and actually like all the stop words usually don't appear in query logs. So if you get your hands on query logs,
so yeah, we have access, but you think to generate a stop word file or what? For what?
Yeah, I mean you get the data what people are really searching for, so you could get your stop words from, but you can also include it into your ranking.
Yeah, we do this. But so you mean the first approach? For the first approach?
Yeah, I mean in general.
Okay.
Like,
yeah, we do this.
You can like also create some relevance score for words based on query logs, seeing which terms are really important.
Yeah. Yeah, we do this.
Thank you for. Hello. Oh,
hi.
Thank you for your presentation. How did you make sure your recall didn't suffer? Because potentially you're filtering out sentences that still have important information.
Sorry again.
So how did you make sure your recall didn't suffer? You're optimizing for improving precision or not losing precision. But since you're using this simple heuristic, right, that if the sentence doesn't have many stop words, then it's potentially not very rich in information. How do you make sure that you're not losing information by using that heuristic?
Yeah, we tested it manually with a lot of data. So we are not 100% sure that we throw away some interesting information, but it's a lot of data, and we are more happy about to throw away nearly about 60 to 80% of the unrelevant data, and we implemented the testing, and it looks pretty good. So I have no exact numbers, but
humans looking at the results and basically making judgments.
Yeah.
Okay.
Yeah.
Hi. Also, thanks.
Hi.
One question about the slide. We mentioned that you return a third of the top candidates. How does Rake do this scoring? And is it done on the sentence level or on a whole document level? So do you have heuristics that the algorithm uses for this scoring, or?
No, the Rake algorithm just calculates the score with term frequency and document frequency and another factor, and then orders the list and then returns 1/3 of the top keyword candidates.
Okay, so for phrases, it just does some combination of those numbers. Okay.
Hi.
Hi.
How does this your solution scale? Because in the beginning you were describing a problem of going from 3 million products to 100 million.
Mm-hmm.
And with this approach, it seems like you can shorten the text, but you cannot keep shortening it, or can you?
We shorten the text. Sorry again.
So
my colleague has an answer.
Yeah, it's just hi, I'm Torsten. It's just one building block to reducing or to increasing the number of documents was, and the first building block was reducing the index size with the existing 3 million documents, and that was a key success. So we could reduce the overall Solr index to gain space to blow up to 100 million products.
Aside from the speed concerns, how do you check you are improving your precision and you are not hurting your recall?
We've got a lot of bad queries, so a list of bad queries, and we just checked these queries, the list of queries, and saw that precision has increased.
Yeah, thanks a lot.
Thank you.